All right, thank you very much all for being here, and welcome to our third sort of software spotlight session for the TYC and the MMM Hub. And so in these, we kind of take a deep dive into a particular software package for materials and molecular simulation that's used, across the country and internationally, and especially on our tier 2 resources as well. And I'm delighted to be joined by Matt Watkins, who's an associate professor at the University of Lincoln in the School of Mathematics and Physics. And Matt described himself as a sort of a long-time user and slight developer of the CP2K software simulation package. And I'm not quite sure what that means, but I'm delighted to have him here. He works a lot on modeling interfaces, especially for electrolytes and solids. And the CP2K package is a wide-ranging material simulation package that can do both sort of molecular finite size systems, but also periodic boundary conditions, solids, and kind of nanoscopic systems, disordered systems as well. Ranging in levels of theory from DFT all the way through semi-empirical methods and towards sort of classical force fields as well, for doing a variety of both static and dynamical simulations. So this follows on from our previous software spotlight packages on DL Poly and OneTep. And yeah, we're very happy to get started with our deep dive into CP2K. So Matt, if you want to share your screen and take us away.
Thanks for that. So I want to tell you a little bit about CP2K. I know that TYC, MMM Hub, there's so many users and developers, it's such a large community that it's a bit hard to know quite what to put the emphasis on when you're preparing a talk. So I'm going to talk about the CP2K code. I'm going to just start off by giving a sort of a moderately in depth, but I'm going to go through the slides fairly quickly. Overview of the core algorithms that it uses for DFT calculations, and I'm going to point out at various points some applications, what people have done with it. I'll signpost to a few extra resources on CP2K. I will try and remember to take a little bit of a break now and then. If anyone wants to jump in and ask any questions, do just type into chat or shout out. So the main website for CP2K, you can find lots of material at cp2k.org. So if I go to the science section, there's a curated list of recent papers, several here, polymerization on surfaces. It's quite an efficient code for moderate throughput calculations. So for instance, for calculating properties of various MOFs or other sort of framework materials, you can do large extended calculations of exploring strain and similar in systems. There's quite a flexible set of tools for performing free energy type calculations. That includes a link into the plumed software infrastructure. And possibly the two things it's most well known for are ab initio molecular dynamics, where it's possible to calculate energies and forces really quite efficiently with a bunch of different Hamiltonians. If you have a system where an electron, there's a balance between localization or delocalization within a system, you often want to do something beyond semi-local DFT. So it's possible to run ab initio MD using beyond the semi-local DFT. So from hybrid functionals, which I'll talk about, through to NP2 sort of post Hartree Fock methods. There's a recent, well, time flies, fairly recent review paper of the methods available in CP2K. So again, you can find the link on the website, but you'll there's an incredible issue of Journal of Chemical Physics getting on for a year ago with review codes from a number of the big software packages, and CP2K was there. You can find quite a lot of details on these methods in that paper. So I'm not going to spend much time saying why we want to do DFT. I'm hoping I'm more or less preaching to the converted here. What we have is a system where we want to be able to calculate the electronic structure of the material. It can be for ab initio molecular dynamics, as I've just said, where maybe the main issue is that there's no reliable force fields available for the system, or you want to probe some quite subtle properties. So you want to be able to use a good quality Hamiltonian, or it might be for molecular or periodic systems. Whenever we calculate the electronic structure of the material, there's a sequence of operations that we need to perform within DFT, at least, that the normal sort of cycle is that we make some guess at the electronic density of the system. Given that density, we construct a cone-sham or a Hamiltonian matrix for the system. We then work out what the eigenvalues and eigenvectors of that system are, or more generally recalculate what the density matrix of that system would be. We then solve the nonlinear problem. We put the new density we've got back into the old system, see whether our densities are converged, and work from that as our ground state of the system. So the steps that are required to do this are essentially the construction of the Coombe-Sham matrix, the Hamiltonian matrix, given our input density, and then the minimization of the orbitals of the density to find the variational ground state of the system. Once you've got that, you can calculate forces, either analytically or numerically, or some mixture in between, which then allows you to move the atoms. So the first bit I'm going to talk about is how the Cohn-Sham matrix is built. And then I will talk briefly about there are standard minimization methods for finding the optimal density in CP2K, but there's also a rather efficient method called the orbital transform, which is very efficient and stable for this ab initio molecular dynamics for systems with a band gap. And then I'm also going to point to some resources and some extra bits and pieces. Right, so the main trick that is used in CP2K to do the efficient DFT in terms of building the Coombe-Sham matrix, it's been used in a few codes like AIM-Pro, around about the mid-90s, these methods started developing it. And what it uses is a mixture of localized basis sets and plane wave basis sets. So what is done in CP2K is to use Gaussian and plane wave representation. So we have a primary basis set. We're going to expand our density of the system on atom-centered orbitals that are a linear combination of Gaussian functions. So on each center, we have a certain number of Gaussians. And so it's a radially exponentially decaying Gaussian function multiplied by a polynomial in x, y, and z, which will give you your different angular momentum types for the orbitals. And then we build a basis function from a linear combination of several Gaussians with different exponents, but with the same angular momentum. So those are the functions that we're going to optimize. And what we want to find is a density matrix in terms of how many of each of these different types of orbitals are we going to use. So an actual basis function is going to be a linear combination of primitive Gaussians, Gaussian function, and then so if you multiply it by a polynomial function, you get a function that looks like an atomic orbital, and we're going to build the density using products of these functions times a coefficient, which is the density matrix. Now these orbitals, these functions are not orthogonal, so we have to work with a metric, with an overlap matrix, which depends on the overlap of the different functions. And then we are building the Kohn-Sham matrix in terms of these basis functions. So we need to be able to calculate the matrix elements of our Kohn-Sham potential integrated between a pair of basis functions. Now we want, I hinted at it, we want a linear scaling build. So we want somehow to be able to reduce the pairs of basis functions down to a linear scaling, a linear set of operations. So Gaussians, in a mathematical sense, will never become zero anywhere. You can go infinitely far away from the center of a Gaussian function, and it will still have some value as the tail drops off. But as far as work in a computer is concerned, we can set some threshold, some epsilon, where below some value we consider the value of a Gaussian to be zero, and then there will only be overlap between basis functions when the centers are within a certain distance. It's going to depend on the exponents of the Gaussians. If we look at a sort of a map with a sort of index of basis functions in the system for the two different basis functions, you see ones that are on the same atom, there's a large overlap, but as we move away, there's only a very few, relatively speaking, functions that actually do have a measurable or significant overlap. And depending on the setting of the epsilon, you can make the overlap matrix that the functions whose the density that comes from a pair of them that we need to consider is far smaller than the potential number of pairs in the system. And so with a careful choice, we can get a sparse representation of the Hamiltonian matrix and the overlap matrix. And this allows sparse matrix algebra to be used in many places in the code. And CP2K's got a specialized linear, sparse linear algebra library called libdbcsr for distributed block compressed sparse row representation of the matrices, and that allows linear scaling matrix multiplication operations. So if you can set up your problem in terms of just performing matrix operations, then you can be linear scaling. And so as long as we can cast everything in that sense, we'll get a linear scaling Kohn-Sham build, and then the issue moves to minimizing the density matrix, finding the best coefficients for these pairs of basis functions. So as we're doing a sort of mixture of theory and practice, there are good quality basis functions for the entirety of the periodic table distributed with the code. The main ones that are used as these so-called molecular optimized Molot basis functions. And what they contain are the basically a list of these exponents, and then a list of these so-called contraction coefficients, which says what are the, for a given function, for a given atomic type orbital, what sets of Gaussians are mixed together in different ratios to give that atomic type orbital. Yeah, it's a bit ugly, but the basis functions that are there for the different basis sets are available. They're just in plain text, and with a little bit of deciphering. You can see the exponents and the coefficients of the different orbitals for the different angular momenta. So we've got these Gaussian basis functions, and then, as was well known from molecular Hartree-Fock codes for many years, you can do analytical calculations of matrix elements over pairs of Gaussian functions. And in particular, you can calculate the kinetic energy and the pseudo-potential terms using analytical expressions for Gaussian functions. So you can write down what the matrix element between a pair of Gaussian functions are for those elements. And as I say, because the sparsity of the system, because the overlap drops off quite quickly, the number of these that need to be evaluated is linear in the system size. Now, there's two more terms in our Hamiltonian that we want to consider. There's the exchange correlation term in DFT, which often has a rather complicated form that we can't very easily work with in the with the Gaussians. There's no easy analytical expression to write down. And there's also the Hartree potential, which is essentially the classical electrostatic interaction of the charge cloud. So how are we going to do those last two terms? Well, essentially, this is where the plane wave bit comes in. CP2K works a little bit like a molecular code using Gaussian basis set, a little bit like a plane wave code with a plane wave basis set. So what is done is to have, as well as this Gaussian basis set, which is the primary one, which is the one that you must be able to represent your density accurately in. Once you've got this this set of Gaussian functions, what we do is project them onto a set of plane waves. So any function you can project onto a set of plane waves. So you set a box, you have a set of regular grids, and you see how much of the Gaussians sit on the various grid points, and you use that to come out with an equivalent representation of the Gaussian functions on the plane waves. And so CP2K actually uses a multi-grid setup. So depending on the exponent, how quickly or slowly the Gaussian decays in real space, you can represent it accurately on different resolution grids. So we typically use 4 or 5 different real space grids. So for sharp Gaussians, maybe semi-valence orbitals, there's very, very fine grid, and then coarser and coarser grids. So what can be done is to project the different Gaussians onto the different grids, and then use so-called restriction and the opposite of it, the special terminology in multigrids, to move the coarse Gaussians up onto the fine Gaussians. If we do that, we've got an equivalent representation of our density in terms of a set of plane wave functions or values on a regular grid. And then we can use all the technology of a plane wave code for that part of the calculation. In terms of the the actual input, the setup, you need to tell it how many multigrids to use, what the cutoff, the energy cutoff is of the finest grid. This relative cutoff says compared to a standard Gaussian, essentially what resolution of grids does the Gaussian need to go on to, and the number of grids is also specified. So once you've got this recipe for putting the Gaussians onto the grid, then we can complete our construction of the Kuhn-Sham matrix. So we've got our density in real space, which was originally represented as a density element of a pair of Gaussian functions, well, a pair of functions that are a linear combination of primitive Gaussians with some weight function, the density matrix element for that pair of functions. And what is constructed is an equivalent function, but on the grid, which is represented by an N with a bar over it. And once you've got the density on the grid, you can calculate things like derivatives of the electron density using essentially finite differences on the grid. You can calculate various terms for the exchange correlation functional. You can work all this stuff in a plane wave grid representation. But then if you want to get back into a matrix element in terms of your original Gaussian functions, you integrate the potential that you had at each of the grid points by the functions. So you switch back between these two different representations. And again, the number of these pairs that need to go onto the grid is linear. Once you've got the grid operations, you can do those. And the final sort of ingredient of this basic operation, as well as doing the exchange correlation functional in terms of gradient derivatives of the density, you can also use the standard plane wave recipe for calculating the Hartree potential. So you convert from an energy expression using the Gaussian functions to our equivalent representation of the density in plane wave basis, and then we do a Fourier transform on that density, and you can calculate the Hartree energy because the Poisson equation for the potential coming from the density is linear, is diagonal in terms of the plane wave basis set. So that's a standard thing. So those ingredients, the analytical representation of the pseudo potential and the kinetic energy, plus the sort of plane wave like representation of the exchange correlation and the Hartree potential, give us this linear scaling build of the Kuhn-Sham matrix. What you see at the end of an output file is a little thing saying how many of the pairs of functions are being put onto the different multigrids, and what you want to get is a reasonable sort of balance across the different grid levels. You can see that this fifth grid is hardly being used here. So there's a little bit of tweaking, or you can just set this relative cutoff high and increase the plane wave cutoff. And it's important to make sure the cutoff is all these representations work as long as the plane wave basis set is good enough to represent the Gaussian density accurately. Time is flying. The other thing you'll see at the end of an output file is a set of timings for the different routines, and this can be quite important for understanding what's going on. So in this case, you can see the building of the cone-sham matrix is taking up a large amount of the total time. So this means that it's perhaps quite a large system in terms of space. There's a lot of plane waves in there, a lot of grid points, and these operations of putting the Gaussian functions onto the grids, and those sort of operations, the Fourier transforms, are taking up a considerable amount of time. And when we're in that regime, we'll find that CP2K is more or less linear scaling, and the actual solving of the cone-sham equations, once we've got the matrix representation of the Hamiltonian, is rather small. But in general, things might change as the system gets larger. I will mention also that we can run in an all-electron mode. So there is an extra set of grids introduced, which are atom-centered radial grids, similar to a molecular code, and there are various tricks allowing that to be run. The defaults tend to be fairly good, and you can more or less just switch from the GPU, the Gaussian and plane wave, to the Gaussian and augmented plane wave methods, and run as an all-electron calculation there. Okay. So the bits I've set out are a recipe for getting the cone-sham matrix. I will very quickly mention the methods available to calculate the optimal density for a given molecular geometry. Essentially, there's two methods, no, three, but there's two standard methods: diagonalization and orbital transformation in CP2K. So again, it's this cycle of take a density, construct the cone-sham matrix from it, work out what the eigenvalues and eigenvectors of that problem are, use that to construct a new density, rinse and repeat until you've got a consistent set. That's the standard method. There are, if I share these notes, there's a more extended version of this from Lian Heng that can be found online. So we're solving the cone-sham problem, we're looking for eigenvalues and vectors of this generalized eigenvalue problem, and the standard solution of that is to convert to a orthogonalized basis with this square root of the overlap matrix, and use that, and then a standard eigenvalue solver. So that's all present in CP2K and standard charge density mixing. The default's a bit aggressive. You want to reduce the amount of mixing between the different iterations, and then it uses this accelerator, and you get a sort of fairly standard output. I'll show an input-output file in a second, and you see the SCF cycle going on. And for a standard diagonalization, you see some initial steps, and then you see the DIS kicking in, and this rapid quadratic acceleration down towards the ground state. The total energy, everything in CP2K is in atomic units, apart from a very few things that aren't, and timings of how long each step takes. And there is smearing. K-point functionality is there, but it's not complete. Now, that is the standard diagonalization. So this is where we're making use of the fact that we're using Gaussian functions, so our number of basis functions is relatively small compared to a plane wave code. So we diagonalize the complete problem and use that to build the new density. The other method that's commonly used in CP2K, so if you've got a semiconductor or an insulator, is the so-called orbital transformation method. So in principle, we've got our energy as a function of the density matrix. And what we're looking for is the density that minimizes the energy for a given system. So if we just find the minimal density, we're done. Why go through all this issue of finding the eigenvalues and eigenvectors? Or we just want to find the best set of density matrix coefficients. Trouble is, we need to keep the Pauli principle satisfied. We need to keep the different eigenvalues and eigenvectors orthogonal to each other, and that gets built in when we diagonalize and we get a set of orthogonal eigenvectors and for the system. So the full problem is a minimization with this constraint built in. But what can be done is to make a clever change of variables. I'm running rather short of time already, so I'm going to skip through this. But you can make a change of variable that will build in this constraint that the Pauli principle is satisfied. What you carry out is a minimization. Essentially, you've got an initial density matrix. There's a thing that you're optimizing, which is always sort of orthogonal in the metric of the overlap matrix to that original thing, and you calculate a new density matrix that's going to be have the correct properties with these constraints built in. And then you can never solve the full eigenvalue eigenvector problem, but you minimize the energy with respect to the density matrix, or equivalently with respect to these molecular orbital coefficients, and you do it directly in this alternative coordinate system. This works very nicely. It does need preconditioning. There's a bunch of preconditioners, and there's normally a couple of different recipes that can be applied. So this is what the SCF cycle, SCF section of the input normally looks like. We have a sort of a restart of the SCF guess. There's a value throughout CP2K. There's this epsilon SCF saying what level of convergence we're after, max number of cycles. The inputs have got a normal sort of nested structure of keywords and sections. So it's an FCF section, and within it it's got a OT section. So it's type of minimizer, the preconditioner, and different preconditioners may or may not have a parameter associated with them. And there's an outer SCF which only applies to OT, and that basically resets the system, calculates a new preconditioner, and starts the problem again. Some of the preconditioners require diagonalizing an approximate matrix, so they're cubic scaling. So as systems get larger, you may want to change to a different preconditioner. And so which of these methods do we want to use? We want to use OT if you can. It's very stable, particularly once it's got found the initial state. It works nicely with several methods for molecular dynamics that allow sort of time reversible propagation of the density from step to step. But it does require an energy gap. It requires at least a moderate energy gap in the system. So diagonalization is the thing to turn to where you've got a metallic system. So, cut down the detail a little bit here. There are all the standard options you expect from moving the atoms. So we've constructed the clean shadow matrix in a linear solving way. There are the ways of minimizing the electronic structure at a given position, this OT or diagonalization. Both of those depend scale asymptotically n cubed with the number of atoms and basis functions in the system, but the prefactor is small. So as you increase the system size, you'll see the scaling, the cost of CP2K changing from linear scaling to cubic scaling. So there's geometry optimization, where you keep the cell fixed and just move the internal atomic coordinates. There's a cell optimization, where you do the same thing, but moving the cell, you can keep the angles fixed, or sort of symmetry of the space group there. There's extensive molecular dynamics capability, lots of different ensembles, MPT, MVT, NVE, etc. There's a rather lovely discussion of really how to do Bellman-Oppenheimer MD from Yokuta, the workshop we did in Ghent a few years back. It's good there. So there's a rather important bit about this time reversibility of the extrapolation of the wave function of the density between different steps that really gives long-term, so sort of nanosecond long Born-Oppenheimer MD capability. There's built-in metadynamics and various free energy capabilities, but there's also a full link to Plumed. There's ASE and AIDA integration, and sort of increasing Python front end for those people that like that. And most of this stuff you can specify with a sort of single command in the video. Right. I suspect what I should do now, given the time, is have a very flying flick through the rest of the slides I've got here, then I'll go on to Young, have a very quick look at the what the input and output looks like there. If anyone does have questions, do just jump in. So I'll share these slides in a bit, so they're more perhaps a bit of a reference than anything else. But it's just a mention of the non-local exchange in CP2K, so how to do hybrid functionals. So there are so-called global hybrids, where instead of the full exchange interaction coming from the DFT, it's replaced by a fraction of Hartree-Fock exchange from the sort of Hartree-Fock level theory. So this has been shown to improve some properties. So just statistically, there's also sort of some theoretical basis for it in terms of adiabatic connection, that you might want to have a hybrid functional. On the other hand, it, in some cases, seems to be less good than modern semi-local functionals, but it depends. It certainly has many useful things. And it comes from this cancellation of the self-interaction correction, where the Hartree-Fock and DFT have sort of opposite properties. So if you mix them together, you can at least empirically come up with something that works quite well. For any hybrid calculation, what you need to be able to do is to calculate all these matrix elements of the Coulomb interaction. Let's say it can be replaced by a screened or other type of interaction between 4 centers. So naively, there's an n-to-4 scaling in terms of calculating all of these exchange interactions. But by various screening methods, you can reduce this down to a linear scaling calculation of the matrix elements. But still, this can be very expensive. because this behavior is only reached really for quite large systems. And for intermediate level systems, there can be huge numbers of basis functions to calculate. So the trick within CP2K is something called the auxiliary density matrix method. And it's this approximation here, I'm not sure how easily it can be seen, that the exchange within the Hartree-Fock method, what we do is we have an auxiliary density matrix that's smaller, or at least is built from more contracted or functions with a larger exponent, so they decay more quickly. And we want to get these two density, the full density matrix from the full Gaussians and this smaller one as close as possible. So if we write this identity that the Hartree-Fock exchange in the larger density is the Hartree-Fock exchange calculated in the smaller density matrix plus this difference of the Hartree-Fock exchange in the big basis minus the Hartree-Fock exchange in the small basis. So this is an identity. These two bits cancel. Now the approximation is to keep this term. So we'll calculate the Hartree-Fock exchange in this smaller basis set, but we approximate this difference in the Hartree-Fock energy between the calculation in the two different density matrices by, instead of doing Hartree-Fock exchange, we calculate some approximate DFT, some semi-local DFT based on these two different densities. And if the density functional recipe for the exchange is able to calculate this difference reasonably accurately, then this thing overall becomes a good approximation to the Hartree-Fock exchange in a larger basis set, and we can dramatically reduce that prefactor that's there. The maths for dealing with these different density matrices gets a little bit convoluted, but it is still a full density matrix, density functional theory. You can follow through the different things. There's different recipes for constructing this auxiliary smaller density matrix. Also importantly, you can calculate forces consistently with this approximation. Again, auxiliary basis sets are distributed with the code, and essentially what you end up with is an input section that specifies that you're using the auxiliary density matrix method. There is how do you do this projection from the big basis onto the smaller basis set, and you also need to define the auxiliary density matrix. The specification of the hybrid functionals can look a little bit scary. It's a recipe that is available. So for PBE, you're specifying the amount of PBE exchange and the amount of Hartree-Fock exchange. So the important thing about running the Hartree-Fock exchange calculations is that all of these four-center integrals get stored in RAM on the machine. So if you run a Hartree-Fock exchange calculation, it will tell you the memory being used by the code for essentially the standard DFT part of the system. The grids, everything like that is distributed so that the cost, the memory size should reduce linearly with the number of cores that you use. And then it tells you the number of four-center integrals calculated, the number that needed to be stored, and the number that need to be stored on disk or calculated on the fly. You don't want either of these things to be there. You want to keep all of the four-center integrals in memory. And then what you'll see is that the first step of the Hartree-Fock calculation, once you've moved the atoms, you need to calculate all these matrix elements. The first step is a little bit more expensive, but then subsequent steps should be essentially not much more than a standard semi-local calculation. So the critical bit is getting it into memory. I mentioned that CP2K is parallelized both using MPI and OpenMP, and it can be important to get extra memory to be able to store these 4 center integrals. So quite often it's worth having 2 or 4 threads per MPI process. So underpopulating, allowing you 2 or 4 times as much memory for the Hartree-Fock integrals. Right, I'm nearly finished on the sort of talky bit. I really have taken a lot longer than I expected. So we could run these hybrid calculations on sort of 1,000 atom systems. This is some stuff we did with Jeff Thornton's group in UCL. So we could calculate polar ion distributions around vacancies on the surface of titanium. We could look at some work from Keith McKenna's group up in York, looking at polar ions and different polymorphs of titanium dioxide. Found some quite interesting materials, so that we could parameterize a hybrid functional that corrected for the self-interaction error when polar ions localized. And as well as hybrid functionals, there are also MP2, GW, RPA, a lot of these things you'd expect. There are dispersion corrected functionals on the website. There's exercises and examples of using these different methods. Stuff that's going on I'm aware of. There's been there have been QMMM methods in CP2K for ages, but there's been a new coupling to the GROMACS code as part of this BioExcel EU project. There's a training course on how to use CP2K coupled with GROMACS offered by the EPCC as part of their Archer 2 stuff. There's new linear scaling methods that are currently done for a type binding, Grimmer's new type binding method. There's time-dependent DFT, perturbation methods. There's various neural net potential implementations and couplings. There's lots of resources up on the website, including videos, a couple I've hinted at, sort of other examples of this, sort of how to use CP2K. Right, if we go over to Young, then we should be able to see that CP2K is indeed there. It's not being very friendly today. There is a supported version, CP2K up to 7.1, which is about 2 years old. And there was a release of CP2K version 9 earlier in January. I need to get that up and working. Unfortunately, the GNU compiler is a little bit old and young. It can be working with Intel compiler, but I need to check which version it's being supported. If we look at an input file, it's essentially these sort of nested input files. So there's a force evaluation section, there's a motion section, and there's a global section. So there's a force eval section, the method using DFT, specify the basis set files, these grids, general accuracy setting, the SCS setup I mentioned, what type of exchange correlational functional you're going to use, specification of the cell, one of the few places where angstroms are used, specify the coordinates, but you can read in from XYZ, CIF file, whatever, and down at the bottom, specify basis sets, auxiliary basis sets if you're using this ADMM method, pseudo potential, tend to use these GTH norm conserving pseudos. Specify the run type, molecular dynamics, the geometry optimization. There's quite a detailed control over what you print out. And for instance, in MD, you can control the ensembles, temperature, etc. And the output you'll get from here. This is printed with more than the average amount of output. It's got quite nice things, units being used. tells you what pseudo potentials you're using, what the basis functions are, plane wave setup, and then you've got the convergence of the electronic structure, and then after a couple of steps of molecular dynamics, it should develop very quickly. This is a benchmarking file rather than the representative. You should be getting down to convergence in a few SCF cycles. It's not using particularly good preconditioner. So nice things, I say, is a timing breakdown. So you can see once you've got some idea, it's be useful to have a slightly deeper one to know what the different things are. Like the Kumsham build is there, but this orbital transformation is taking maybe half the time. So this is somewhere in between. This is for our 256 molecules of water system. So it's a balance between the density matrix minimization and the construction of the Kumsham system. It prints out a set of references. So whenever you activate a given algorithm in the code, an appropriate reference comes out. It's quite useful. Some stuff about the message passing, so how well the communication is working. The grid count, which I mentioned for the multi-grids. And there's some extra info on this sparse density matrix, sparse matrix library. And for the various other subsidiary files that come out with a prefix of this project code in the input file. Right, I realise I've whittled on way more than I meant to do, so I shall stop at this point. If anyone's still awake and wants to ask any questions, please do so. I apologise, I had quite a few technical problems which discombobulated me a little bit at the beginning. Otherwise I'd probably be a bit more sort of on time, but thanks very much for listening, and I'm around if anyone wants to ask anything.
Excellent. Well, thank you very much, Matt, for that overview of CP2K and its functionality. The floor's open for a few questions if people have any. There's already a couple of comments from Heather Kelly in the chat. Heather says, we do have the new compilers on Young if you want to load beta modules first. And apparently there is also CP2K 8.2 already installed, I think, possibly as a module. So a slightly newer version then, although perhaps not completely up to date, but you can load the new compilers if you want to install your own version of CP2K then. So yeah, please stick your hands up or put into the chat if you have any specific questions about CP2K. I just wanted to ask a couple very quickly. You mentioned about the Molot basis sets that you use. Are there associated pseudo potentials that are designed to go with them?
Yeah, so that there's a basis set library as well. Sorry, pseudo potential library for most of the functions as well. Yeah.
Okay, fantastic. I also just wanted to ask about the license of CP2K. Is it free for anyone to use and download?
Yeah, it's absolutely free. So it's GNU. Well, some bits are now. It's all GPL apart from a few bits that are BSD that are coming in. We'd like to be more open, and indeed, it's open development and source. You can just go and look on GitHub for the latest versions.
Fantastic. And then a slightly more general point. I don't want to be sort of pitting codes against each other in any sense, but I guess it's useful for new users that are perhaps agnostic to which code they want to use, perhaps to think a little bit about, what perhaps what you would think the USP of CP2K might be compared to other codes, like for instance OneTep. Obviously, the underlying basis is different, and obviously this sort of Gaussian and sort of plane wave dual basis is something that is probably more developed in CP2K than perhaps any other. But how does that translate into, you know?
So CP2K has a lot of stuff in there. I mean, a lot of people, it is open development, so a lot of things have gone in. So there's some, you know, a lot of things are there if you dig. What works out of the box very efficiently is sort of medium-sized systems, and particularly medium-sized systems with hybrid functionals. So with a bit of tweaking, if you want to run, let's say 500, 600 atoms with a decent quality hybrid functional, I think, you know, you'd be struggling to find a more efficient code. It's also good for long-term ab initio molecular dynamics. Those are perhaps the two things that are really, really strong. There's lots of other stuff there, but those are headline ones.
Okay, that's good to know. And is that true even for crystalline materials? Because obviously you don't have K-point support, or as you said, I think it was quite nascent.
So this is the you know, the sort of the slight Achilles heel. It was mainly designed originally for biosystems, for molecular dynamics. It's got a lot of strength. You can do a lot of great stuff in solid state, but the full K-point support is not there for everything. So it doesn't for hybrid functionals. So really, you need to be able to run at a gamma point to get the full efficiency. So if you've got at least a moderate band gap and gamma point is a good representation for your system, then and the hybrids work well in the in a periodic system.
Excellent. Okay, fantastic. Are there any other questions from anyone in the audience that want to ask about CP2K? Ed?
Hiya. Yeah, thank you very much for a really detailed talk, and yeah, really nice to see the background and an example. I wanted to ask about if you knew about the GPU support, you know, what's currently possible and what's going to be moving in. On Young, we're looking at basically two nodes that are going to be GPU based, and I wonder if that's something that we could exploit with this code, or if it's mainly CPU.
So again, I think this is a challenge for a lot of DFT codes, because it's not just one routine. You know, DFT codes run through a whole bunch of different stuff. So in CP2K, the sparse matrix library, DBCSR, should be fully up and running with multiple GPUs per box. So the sparse, anything that relies purely on sparse matrix operations should get a big boost straight out of the box. So there's some linear scaling methodologies that use, so if you can stick in matrix multiplications, then you should get there. There is work ongoing on building in a sort of an offloading infrastructure. So this mapping of the Gaussians from the local basis sets onto the grids. So there's some new code from Molot, which provides a generic offload into a bit of C that allows you to then distribute those Gaussians and the grid points onto the GPUs. And again, that should start to be seeing some considerable speed up. There are also a different algorithm for calculating the 2-electron integrals for post-Hartree-Fock stuff, so MP2 and RPA. And again, those things rely, this conversion between the molecular orbital and AO basis sets, that stuff is again matrix multiplication, and that should, so the answer is there are lots of probably at the moment out of the box we're not going to get good performance for the whole of the algorithms for many modes of operations, but there are several bits of it that should be good for benchmarking and seeing where it's really working well on GPUs. and it will be really nice to see which bits are holding up, and trying to come up with a strategy to fill in those gaps.
Okay, amazing. So people potentially should just try that out if they think. I mean, from what I understood of your benchmarking, that looks like the majority of the operations are kind of matrix multiplication in some cases. So it'd be worth people just trying that to see if it gives them a speed up.
Yeah. So if any system where you're mainly sat in those sparse matrix algorithms, then you should be getting a proper speed up out of the GPUs.
Fantastic.
Thanks, Ed. Just to follow up on that quickly, it sounds as though maybe going to a full linear scaling algorithm, you know, might be the way forwards there. Then it's all just matrix multiplication. No
yeah. So it is. That's there, and there's some. I'll put a link to an archive paper. There's a very nice new method developed by some guys in Paderborn that looks really promising for really working very efficiently. The trouble is that linear scaling is great, but then you tend to lose some of your analysis tools. You can run a really big system, but then you want to start asking questions. You want to be doing perturbation theory on it. You want to be doing it. You want to do lots of stuff on top, and a lot of the algorithms need to be rewritten then. So it's yes, for just pure
energies, it's fine, but if you want forces and everything else, yeah.
And it can be done. I mean, there's great stuff in one tech. There's lots, you know, but it's all. You don't just redo one bit. You've got to sort of rewrite sort of lots of other stuff as well. So yes, but no, but yes.
Yeah. Excellent. Okay. Are there any other questions? Anyone that wants to stick up a hand or ask a question in the chat? If not, I would like to thank Matt again very sincerely for a great talk. We've recorded this, you know, this event, and it will be available on the TYC website and the MMM Hub website as well. We'll distribute it more widely as well. And do point your students towards it if they want to have a little bit of an introduction to CP2K and its capabilities. And hopefully we can encourage more adoption of these codes from these events. Okay, thank you once again for attending, and thanks again to Matt for the presentation.
Oh, thanks for inviting me, George.